moving forward. Okay, so rate laws and rate constants. All right. So as was pointed out here, when I have, so at any point along this reaction, the slope represents the rate. Okay. And maybe you remember from Chem 110, maybe not. We had this thing called the initial rate, which the initial rate would just be the rate initially, right? Okay. We have what would be called the average rate. And so the average rate would be if I looked over a much bigger range. So my average rate would be, let's say if I looked at this point all the way down to this point and just calculated, the change, the rise over the run, okay? That would give me the average rate. So if I looked at that over that would give me the average. And if I looked at this point, what's saying right here, that would give me the instantaneous rate. All the same, hopefully what you realize, what you're seeing is all of those rates would be different depending where we are at in the reaction, right? The initial rate would look much larger than perhaps this instantaneous rate at a later time in the reaction, okay? So that's why we use what's called a rate constant, which will have a constant value across the whole time series of the reaction, okay? So let's do an example, another generic example. A plus B goes to products. And what I want to say with rate laws, okay, it's all about the reactants, okay? We're going to have to start getting used to seeing that, all right? It's all about the reactants. And obviously we can still do the rates of the products, okay? But when we set up these rate laws, it's all about the reactants because those are what's easiest to measure, right? We have finite amounts of reactants at the start of a reaction, but more often than not, we have zero product at the start of a reaction. So it just becomes easier to monitor the rates of reactants, okay? So it's all about the reactants, all right? So we could start by saying that rate equals negative dA dt, which we recognize from the stoichiometry. B will have the same rate, okay? So that's all good. And so now the way I can make a rate law out of this thing, I'm just going to use the generic rate, knowing that I can either set this equation equal to negative dA dt or negative dB dt, because both are reactants. And what I do to set up this rate law, it's always going to be K times the reactants. So K times the concentration of A raised to some power that I'm going to talk about soon, times the concentration of B raised to some power. So this is how we always set up a generic rate law. So this gives me my rate law. And so if we had a third reactant, if it was an A plus B plus C, then I would also have a times the concentration of C raised to some power, okay? So K is the rate constant. And as we shall see, the rate constant has the same value throughout the entire reaction. So it's basically a proportionality constant for rate and concentration, okay? And then finally, those little superscripts that I put up there are what's called the reaction orders, okay? So that would be the reaction order of B, and that will be the reaction order of A. And this is the complicated thing of kinetics is in equilibrium, we often just look at the stoichiometry and we get what those coefficients should be. They are the stoichiometric coefficients. Reaction orders are not necessarily the stoichiometric coefficients, okay? As it turns out, They are the stoichiometric coefficients when you have an elementary or a fundamental step, okay? But if you don't know what the mechanism is, if you don't know what the fundamental elementary steps are, then you can't say that these reaction orders are equal to the stoichiometric coefficients, right? You have to do the experiment. So reaction orders are often determined experimentally. Okay. Now you can also determine reaction orders from a complex, detailed study of the mechanisms, which would be theoretical. So you could do a theoretical study of the mechanism and determine the reaction order. However, that's hard. That's really hard. So we often always determine reaction orders experimentally. And I think I have that. Oh, look, I have a whole slide that says reaction orders that I didn't even use. All that stuff I just said, put it in here. So reaction orders, let's just do that, are determined experimentally or with a detailed, and I'll put theoretical, examination of the mechanism. And we're eventually going to do that. We're going to be able to do that soon. Okay? But the way that we often start this determining reaction orders is by looking at experimental data.